Hello and welcome to this math video on solving a triangle with side-side angle when ambiguous case exists or possibly exists, but these three examples it's going to exist. So we're going to be looking at in our side-side angle chart that we previously made where angle A is acute and the opposite side is smaller than the adjacent side. In all other cases, it's not ambiguous when angle A is obtuse, if you remember. So long as A is bigger than B, you get one triangle. If angle A is right, the same case exists. So long as A is greater than B, you get one triangle. If angle A is acute and A is equal to B or greater than B, then you only get one triangle. But when A is smaller than B, there are three possibilities for which we have to test the height to see if we get no triangles, one triangle or two triangles. Remember, if we do the height with B sine A, and the height is exactly equal to the length of that A opposite side, that means that A opposite side is actually right here, and you have one triangle, which is a right triangle. If A is smaller than the height when you calculate the height, then you have no triangles possible because that A will just swing back and forth and never touch the bottom ray of the angle. If A is larger than the height, but still smaller than B, because that's the case we're looking at, then you have two triangles possible, one where A hits to the right of H and to the left of H, creating two possible triangles. And we derived all of this in our previous examples and in class. I have an example of each here. One where you end up with one triangle, one where you end up with no triangles, and one where you end up with two triangles, and we'll solve out the triangles. So let's look at our first ambiguous case example. We have angle A is 30 degrees. The opposite side is 4, and the adjacent side is 8. I'm not going to fool with units here. We're worried about the mathematics of it right now. So we're going to calculate the height of the triangle to see how H compares with the opposite side of A. So to get the height is equal to B sine A. That's going to be 8 sine 30. All right, we all know the sine of 30 is 0.5, but we can see that here anyway. Sine of 30 is 0.5. So 8 times 0.5 is 4. That means the height is 4, which means the sine of A, or the side A, is actually right here. And we get one unique triangle, which is a right triangle. And we can easily solve that out. So here's a picture of our triangle. Now, if you recognize this to begin with, you knew there was going to be one triangle, because with a 30-degree angle, this has to be 60. We have a 30, 60, 90 triangle in which the opposite side is the smallest leg, so the adjacent leg is 4 times square root of 3 using our 30, 60, 90 rules. So on this one, we got one unique triangle. And there it is, all solved out. In our second example, which I would encourage you to determine the number of triangles possible on your own, maybe solve them out. You could pause the video and come back. But if not, you can continue watching. Okay, I said we were going to have an example of each. So this is either going to be no triangles or two triangles. 9 and 14. So let's calculate that height. The height is B sine A. So I'm going to do 14 times the sine of 48, and I get 10.4 on the calculator. 14 sine 48 is about 10.4. Uh-oh, 9 is shorter than 10.4, so it won't even reach the bottom side of this ray, this undetermined length that we can play with. It's just going to swing back and forth and back and forth, and we will never even get a triangle, so we don't have to solve this one. It's nice when you get no triangles. No triangle possible on that. So we don't have to solve them. We can go to the next one. Cannot create a triangle with that case. So the third one, again, I would encourage you to work to this one, and you can tell because the other one had no triangles and the first one had one triangle. This is probably going to be the one where we have two triangles possible. So go as far as you can. You could pause the video or you could just continue watching. Recommend any triangle you get, you turn it around where it's facing like this. There's something to be said for what you're used to. You can change what you're not used to into what you're used to if the triangle's flipped around. So we have to calculate the height to see if 11 is bigger or smaller than the height. But of course it's still less than b, so there's no way it's going to be going over here somewhere. b sine a, so that's 13 sine of 50. 13 sine of 50 on my little calculator here is 9.95, so essentially 10.0 if we round to the nearest 10. So we're going to say approximately 10.0. In any case, A is smaller than that height. So we're going to get one triangle that has 11 here, A, C, B. So I'll call that B1, not B prime. Or 11 as a radius of a circle could come over here. We'll call this B sub 2. I should be using sub, not exponents. Because subscripts are for naming in math. Superscripts are for other things. So we have B sub 1 can be over here, or B sub 2 can be over here. Now at this point I've kind of got a messy picture. It's got a lot of stuff. I'm going to, since I have two triangles, separate them and look at each one separately and solve for the complete two possibilities. So we have triangle A. BC could be this one, in which the original information still holds. This angle is 50, this side is 13, and this side is 11. Or this triangle, in which, of course, A is still 50, this side is 13, this side is 11. And this will be the other possibility of where B is. Now, when you use your calculator, of course, we're doing law of sines here. The ambiguous case falls in law of sines. To solve this triangle, you're going to get the acute angle first with law of sines. So if I set up a law of sines here to solve for angle B, sine of 50 over its opposite side is going to equal sine of B sub 1, or whatever point you want to call it, over 13. What we call it is not important. So I am going to solve this proportion here. The sine of B is equal to 13 sine 50 divided by 11. Now since this is the sine of B, we should get something between 0 and 1. So the 13 sine of 50, I still have in my calculator from before where I did B sine A, is 9 point, I'm going to go to 4 decimal places instead of rounding it to 10, 9586. Oh, and I still have to divide it by 11 now, so I'm going to go ahead and divide it by 11 before I write it down. 0.9053. That is the sine of angle B. So to get the measure of angle B, we do the sine inverse of 0.9053, and we get that B is about 64.9 degrees, 64.86. So this angle is 64.9 degrees. I could finish solving out this triangle with another law of sines to get the bottom side what it could be. So I'll do another law of sines with this. So I'm going to say sine 50 over 11, I'll use that, equals sine of, oh, I need angle C to do this. Well, I'll just take 180 and subtract these two angles. So in my calculator, 180 minus 50 minus 64.9 is 65.1. So sine of 65.1 over the missing side AB1, which I should have just called C, but whatever. So 11 times sine of 65.1 divided by sine of 50 is, that side C is approximately 13.02, so about 13.0. I better say 02, because I do, if you look at this, well, 13.0 is fine. Yeah, it's 13.02 or 13.02. Oh, like we're dealing with a triangle here, which is essentially isosceles. We're finding out 64.9 and 65.1 degrees are so close together. It's almost like both these angles are 65. So I guess it shouldn't be a surprise that both these sides turned out to be essentially equal. That will not be the case all the time, as you can recall from the examples we did in class, but we are essentially dealing with an isosceles triangle. It's so close to isosceles, it might as well be considered, for all intents and purposes, to be isosceles. I didn't expect that to happen. Kind of threw me for a loop in a minute. That happens sometimes, though. Sometimes you can get an isosceles triangle. So notice how after we found that first angle, we were able to just use triangle angle sum and law of sines over and over and over again until we got the triangle solved. Great. Now we have to solve the other triangle. And getting the first angle in that, it's very helpful to go back to your original picture. And this is what we did in class. If this angle is essentially 64.9 or 65 degrees, this angle is the same. Like this is this angle in the big triangle. That's what we drew out. We drew out that triangle. We also drew out the triangle on the left. So this triangle here is this one. And the big triangle here is this one, which turned out to be isosceles. Turns out that this side and this side are the same length, and that our original picture doesn't show that because we didn't know it at the time. So this angle of 64.9 right here actually can go right here. So the triangle between the two triangles is isosceles, the one that's not one of our two triangles. So this angle is 64.9. And this angle, which is the angle in this triangle, we can just get as a supplement of 64.9. That will always be the case. Whatever you get for this angle will end up being the supplement of it. So I'm doing 180 minus 64.9 in my calculator, and I get 115.1. So now I can just do some law of sines and finish out this triangle. Let's find this third angle up here by subtracting from 180. 180 minus 115.1 minus the 50 degrees at angle A leaves me with 14.9 degrees. I can set up a law of sines to solve for this side down here. So sine 50 over 11 equals sine 14.9 over C. I get 11 times sine of 14.9. And then I'm going to get that and take it and divide it by the sine of 50 in my proportion. And I get 3.69, about 3.7. C is approximately 3.7. So this ambiguous case in which I got two triangles, both triangles have been completely solved. All the sides and angles are labeled. I have two triangles.